So, last class we were talking about the glass formation and the various criteria of glass formation. We talked about the thermodynamics of glass formation, we talked about the kinetics of glass formation. As you can see here, what we have is the critical cooling rate, which talks about the kinetic constraint. That means if you can suppress the crystal, you can get a glass. And this is for getting a bulk metallic glass that one can have if you can have the crystallization more difficult in some systems, you can have crystallization, glass formation at a very slow cooling rates, and that is what is a bulk metallic glass or bulk glasses in silicate systems that we have seen. We have also talked about fluxing the glasses liquid to get a higher glass forming ability. We started talking about the Cosman paradox. You know that if you can take a liquid, keep on cooling it below a certain temperature, once you come to a certain temperature, the entropy of the liquid goes below that of the crystal, which is a paradoxical situation, and at that condition the liquid will undergo a glass transition. This is what is called ideal glass transition temperature, Tk, or the Cosman temperature. We also talked about the entropy catastrophe. That means if you take a solid, keep on heating it to above the melting point, the entropy of the solid keeps on increasing, and once you reach a particular temperature, which is called the TSI, or the entropy catastrophe temperature, at that temperature the crystal will have higher entropy than that of the liquid, which is again a paradox, and as a result crystal will catastrophically melt, and that's a situation which is usually not observed in practical applications because the temperatures that you need to go are much higher than the melting point, which is not usually possible. So we talked about this. We also talked about the possibility of various temperatures at various under different conditions. For example, the observation of, you can see here, the melting point, which is the TF, and if you keep on going below the melting point at the temperature Tk, one thing that you need to see is that last class there was a kind of a confusion among this delta G, whether it should be 0 at Tk, because we are talking of this delta G, which is the delta G between the liquid and the crystal. We are not talking of the delta G between liquid and the glass. Okay, so what is being plotted here is the liquid and crystal. Okay, so free energy of the liquid and free energy of the crystal. So because we are talking of the free energy of the liquid and the crystalline solid, so as a result this free energy of the crystalline solid is always lower below the melting point. As a result, if you talk of GL minus GS, GL minus GS is always positive at temperatures below the melting point, and that is what we are plotting here. And once you come to a temperature below Tk, it falls down, but this part is shown dotted because once you reach Tk, already the glass forms. So there is no question of talking a temperature below the Tk, because by that temperature the liquid has already transformed to a glass. So there is no liquid left out for it to become a crystal. Okay, so if you talk of any temperatures below Tk for the liquid to be undercooled below Tk, we cannot undercool liquid below the Tk, because once you undercool a liquid to Tk, by that time the entropy catastrophe comes into picture, or the Cosman paradox comes into picture. So liquid cannot remain as liquid, and it immediately transforms to a glass. And once it has transformed to a glass, it is a glass that we have and no more a liquid. So we cannot still talk about the free energy of liquid below the Tk. So as a result, though thermodynamically one can really calculate that free energies and talk about what is called a T0 temperature, that T0 has no meaning, because by the time you reach Tk, already a liquid has vanished, it has transformed to a glass. So there is no liquid left out for it to transform into a crystal. So as a result, we show this part dotted. Similarly, if you are on the other side, above the melting point, if at all you can heat a crystal above the melting point, keep on heating the crystal above the melting point, the free energy of the crystal will be higher than that of the liquid above the melting point, and as a result the delta G will be negative, because we are showing delta G as GL minus GS. You can see here, okay, because it is GL minus GS, GL is smaller than GS above the melting point, this part is negative. But as you keep on increasing the temperature, we have, as we saw in the previous slide, the the entropy of the solid keeps on increasing, and once you reach a temperature TSI, at that temperature you will see that the entropy of the solid will become equivalent to that of the liquid. So even though the delta G is negative, that means free energy of the solid is higher than that of the free energy of the liquid there at that particular point of time, but because of this entropy paradox coming into picture, the crystal cannot remain as crystal and it has to catastrophically transform into a glass. So that is what would happen. For example, we have seen a number of cases, you can take a crystal, keep on bombarding it with some kind of ions, and we know that you can keep on increasing the defect concentration in it, and as a result the free energy increases, and as the free energy increases the crystal will have a high free energy, but at the same time the entropy will be so high in the system that it can transform to an amorphous phase beyond a certain critical concentration of the defects. Okay. So though at the conditions here, as you can see, the free energy of the solid is higher than that of the liquid, but we reach a condition where the entropies become 0, and once this happens the crystal is no more stable. So but anyway, this is a temperature which is only theoretically possible, but practically reaching this temperature is very difficult. So usually in textbooks you don't come across this. Okay, there are a lot of people who are doing research in this area, but basically you do not talk about this, whereas TK is to some extent achievable, and in a number of systems we have achieved the liquid and in glass condition below the TK or TG, whatever you want to call it. Some people refer to it as TG, glass transition temperature, some people call it as TK, which is Cosman temperature, but both are basically the same. Okay. Only difference is TG is the one which we usually measure when you take a glass and start heating it in a DSC, and it shows you a hump. I showed you a small step, and that step is what is called the TG, which is the second order transition. Okay. Whereas here the TK that I am talking is during cooling, the liquid is being cooled and you reach a temperature where the entropies gives you a paradox situation, and that is where the liquid transforms to a glass. So one is on the heating side, we are talking about it, but another is on the cooling side, but basically both are the same. The temperatures are more or less the same. So we started talking about the T0 concept in the last class. We know that if we are at any composition which is on the left side of the intersection of the free energy of the liquid and that of the alpha, at those compositions the alpha can come out of the liquid with the same composition, because there is a driving force for the alpha to form from the liquid having the same composition. This is what we call partitionless solidification. Whereas if the composition is on this side, on the right side of the T0 point, we see that there the alpha cannot come out of the liquid, so the liquid will remain as liquid. In fact, for people who are interested to produce partitionless solidification, to have partitionless solidification, why do you want to have partitionless solidification? If you want to have solid solutions with extended solid solubility, we would like to have partitionless solidification. If you have extended solid solubility, as I told you, you can have higher solid solution strengthening. At the same time, by precipitating a second phase, you can have large volume fraction of the second phase. We talked about it earlier. So everybody would like to have large partitionless solidification, large range over which partitionless solidification can occur, or the solubility to be extended to as high value as possible. That means this T0 to be shifted to the higher concentration of B. But this is as far as if we want to get a solid solution. But if somebody is more interested in getting an amorphous phase, he wants this point to be shifted to the left. If this is shifted to the left, what does it mean? That means the composition range over which liquid is more stable increases. If this curve, if this point, which is the T0 point, if this is shifted to the left, okay, that means that is a situation where the liquid is more stable for a large composition range. If the liquid is more stable, what is the advantage? The advantage is if I can keep that liquid stable up to a temperature which is the Tg, then that liquid will undergo a glass transition and I will get a glass. So, if you want to get a glass, the first thing is that liquid should have higher stability. The stability range of liquid should be higher. So, you have to somehow make liquid more stable. If you can make the liquid more stable, then there is a chance for you to get a glass. So, as a result, you can see here this is the domain that we are interested. That means the domain which is on the right side of the T naught is of interest to a person who wants to get a glass. The domain which is on the left side of the T naught is of interest to somebody who wants to get a solid solution. Okay? So, if you go to enlarged portion of the phase diagram and talk of the two T naught curves, one which is corresponding to the alpha, the green curve here, this is nothing but the T naught alpha, and here on the left right side you have another T naught, another green curve which is the T naught beta, we call it. That means the T naught of the liquid with respect to the beta. That means the compositions and temperatures where the free energy of the liquid is equivalent to that of the beta. What is T naught? T naught is nothing but the trace of all those temperatures and compositions where the free energy of the liquid is equal to some solid, whether it is alpha or beta or gamma or whatever it is. You understand? So, and that T naughts, if you plot both the T naughts, the region which is between these two T naughts is the region which is of importance to somebody who wants to get a glass, because as I told you before, it is on the right side of the T naught where the liquid is more stable. That means this is the domain where the liquid is more stable, and to the left side of the D naught for this T naught alpha, and to the right side of the T naught for the T naught beta, it is the alpha and beta that are more stable. So, for getting glass, it is this region which is important, and within this region, if you can somehow undercool the liquid, let us say take a eutectic liquid, bring the eutectic liquid below the Tg, and if you can bring it below the Tg, then you can get a glass. You understand? So, this is the very crucial domain for glass forming, and so if I can say what is the glass forming range for this particular phase diagram, the glass forming range is starting from this point to this point to this point. So, that means the domain between the two green curves is the glass forming range. The composition range between the two green curves is the glass forming composition range. That is what we have talked in the last class also. And try to see some other examples of such a thing. Here is what we talk about deep eutectics and shallow eutectics. Take another free energy phase diagram. This is one example of a phase diagram where a eutectic phase diagram, T naught alpha is drawn here, T naught beta is drawn here, the dotted lines or the dashed lines I should say, the dashed line here and the dashed line here, these are all the T naught curves, and the distance between the two T naught curves will give you the glass forming composition range. So, if the liquidus is very sharp, then the T naught will also be very sharp, and as a result you will get a very large glass forming composition range. But if you have a situation where the liquidus is very shallow, then the T naught will be shallow and the T naught of beta will also be shallow, and both of them might intersect, or in this particular case you are seeing only one T naught. Why do you see only one T naught? Because the structure on this side and structure on this side is the same. This is an example of, for example, we talked in the last class about a system, do you remember? A system where you get a eutectic silver copper, correct. Silver copper is an example where you have silver of the FCC structure, copper of the FCC structure. So, if I draw the T naught will basically merge, because there is only one free energy curve. There are no two free energy curves. It is not that alpha curve and beta curve you have. So, you have one free energy curve for alpha and one free energy curve for liquid, and because of which you will get basically 1 T naught, continuous T naught. And in such a case, then there is no composition range where glass can be stable. So the glass forming range in this case would be almost 0. So there is no glass formation possible, because for glass to form you have to bring the liquid below the glass transition temperature, and glass transition temperature usually is somewhere below here, and the T naught curve is above. If the glass transition temperature is below the T naught curve, you cannot have any glass, whereas if the T naught curve goes below the TG, then you can get a glass. So glass transition is possible, or glass formation is possible in any phase diagram where the T naught curve will intersect the TG. If the T naught curve does not intersect the TG, if the T naught curve is above that of the TG, if both the T naughts are intersecting above the TG, then you will never get a glass. If both the T naughts are intersecting below the TG, that's when you will get a glass. That means you will have a situation like this. If I draw if this is the T naught and this is another T naught, if these two are intersecting above the TG, this is T naught alpha, this is T naught beta, let us say, this part is not there. Okay. So if that is what is happening, then you will never get a glass. But you can still say, yes sir, in principle every liquid should become a glass. That is the kinetic part of it. This is what thermodynamics tells us, that if the T naughts are intersecting above the TG, you should not get a glass in principle. But if I take that liquid and cool it so rapidly that no alpha or beta can nucleate at cooling rates such as what we experience in laser, in such a case the liquid has to remain as liquid till you come to very low temperatures, and then you get a glass. So in principle every liquid can be made a glass if you consider the kinetic aspect. Okay, and this is what thermodynamics tells. So thermodynamics basically is useful when you are comparing two systems. When I am comparing two systems, I can say this alloy is easily glass formable. Okay, it can easily form a glass than this alloy, or this particular system is easily amenable for glass formation than this. So which has a higher glass forming ability? This is what, for comparing the two systems, one can use a thermodynamic approach to, for example, shallow eutectic, deep eutectic. We can say easily if a liquid, if a particular phase diagram is a deep eutectic kind of a phase diagram, we will come to them a little later, we can say easily you can get a glass. Whereas if it is shallow eutectic, we will say it is more difficult for you to get a glass, but at the same time I will never rule out that you can never get a glass. Okay? So keep this in mind. Then this is another example where all kinds of curves are shown here, the T naught curve which you have and the TG, and here if you see various domains are shown. What is this domain on this side? This where alpha is written. Can you tell me what is that domain? This domain which is enclosed within that alpha region, that is a stable alpha region where the alpha is stable. That means on the left side the terminal solid solution alpha is stable. And if you look at the T naught curve and you have another hazed portion there, the vertical lines are drawn there, and that portion, if you consider, what is that portion? It is metastable alpha. There also alpha is possible. If you can undercool the liquid from above the melting point, from above the liquidus tank, and come to a temperature below the T naught, yes, alpha is possible, and that is a supersaturated alpha, which is not a equilibrium alpha. You will get that only under fast cooling, whereas this alpha, which is the terminal solid solution, is a equilibrium alpha. So alpha is possible even beyond the equilibrium solubility range, and that is what is called metastable alpha. And above the T naught curve, what you have is the liquid which is metastable liquid, and once you come below the TG, that metastable liquid will undergo a glass transition, and that is a glass. And you also see another curve here which is called T mu. that is the T mu is related to the shear modulus. Okay. For any given composition, one can calculate what is the temperature at which the shear modulus goes to 0. From that concept of view, this is the particular temperature where the shear modulus goes to 0. So this is the mechanical definition of the melting point. So how the melting point changes as a function of composition, one can talk about when he considers not from the thermodynamic point of view, but from the shear modulus point of view, because we know that shear modulus goes to 0 above a particular temperature. But usually you do not come across this, because before that the thermodynamic melting point comes into picture and then immediately the liquid melts there. In principle, if the liquid does not melt here, if you keep on heating the solid, once you reach this particular temperature, that is where the solid will melt. But then there are a number of melting points that can be possible. People talk about hierarchy of melting points nowadays. For example, the entropy catastrophe is another melting point. If you keep on increasing the temperature, first melting point that you will come across is thermodynamic melting point. The second melting point that you would come across, if at all you can suppress melting at that particular thermodynamic melting point and keep on increasing the crystal to higher and higher temperature, once you reach a the what is called TSI, which is somewhere between the T naught and T mu, it will always lie between the T naught and T mu, and that is the temperature where the entropy catastrophe comes into picture, and the crystal will undergo a liquid, it will catastrophically become a liquid. If you somehow suppress that, which is impossible, then you can still go ahead, then you will come across the shear modulus going to 0, and that is what is the other catastrophe comes into picture. So nowadays the people, these are all theoretical concepts, but practically reaching those temperatures are very difficult, but physicists work on all this kind of possibilities, and in principle these are all possible. And this is another situation where we can combine the glass formation both from the liquid and from the crystal. That means solid state amorphization and amorphization from the liquid can be combined in one diagram. What you can see here is what you are seeing, the T naught curve and the TSI curve, which is the entropy catastrophe curve, and the TG. What we see is that if you take a liquid, come below the TG, you come to a glass. This is similar to when we talk about for example, you remember we draw the phase diagram for the water, this kind of a phase diagram, that you have the solid, which is the ice, and water and steam. There is a triple point we talk about. Similarly here you have a triple point, the liquid, the crystal and the glass. This is the triple point. What we basically mean here is, if you take the liquid, come below the TG, you get a glass. If you take a crystal and keep on increase its concentration in a rapid fashion, then that crystal can become a glass. This is what we see in a solid state amorphization. That means you take a crystal, allow one of the element to diffuse very rapidly into the other. In such a case, then the element, the solute element rapidly diffuses into the solvent element. I told you anomalous diffusion of one element in the other, and in such a case then the concentration rapidly increases, and once it crosses a certain critical concentration, the crystal is no more stable because of the large number of defects that are introduced because of this rapid movement of one of the element into the other, then the crystal will become a glass. You can also have liquid becoming crystal if you come below the T naught. Either you bring that liquid below the T naught, you get a crystal, and the take crystal again above T naught or TSI, you get a liquid. T naught is the thermodynamic iso-free energy, TSI is the iso-entropy. That means here is the catastrophic melting taking place, here is the thermodynamic melting takes place. So if you take a crystal, keep on heating it, come to T naught, you will get a normal thermodynamic melting, but instead of that, if you somehow suppress melting at that point and keep on increasing to a higher temperature, once you come across TSI, for any given composition, you will see that crystal will undergo a catastrophic melting and will become a liquid. So you can see all transformations here, liquid giving you a crystal, crystal giving you a liquid, and crystal giving you a glass, and liquid giving you a glass, and glass again giving you a liquid. This is what we see when we take a glass and keep on heating it. I told you before, if you take a glass and heat it in a DSC, what you see is beyond the TG, below the TX, you have a region, this region. What is there in this region? Can somebody tell me? What you have there is a liquid. What is this glass transition? What is the glass transition? Glass transition is where the liquid transforms to glass or glass transforms to liquid. It is a transition between liquid and glass. So it is not, no crystal is forming at this temperature. As I am heating a glass, I am taking a glass here, heating this glass, the moment I reach the TG, at that TG glass will undergo a transformation and gives you what is called a supercooled liquid or undercooled liquid, because liquid is not stable there. So it is an undercooled, because we are still below the melting point. So it is a supercooled liquid, and once I come to a TX, at that TX this supercooled liquid will undergo a crystallization, because at that temperature liquid is not stable. So liquid is above the TG. If it was below the TG, it would have transformed to glass. Already we are starting with a glass and heated it above the TG, so liquid has formed, and this liquid is a metastable liquid, it is not a stable liquid. So this liquid has to undergo a crystallization, and that is what you see here. And this particular range is called delta Tx, which is a very crucial parameter, which is called Tx minus Tg, which is a parameter which can measure how easily a glass can form or how stable is a glass. For example, if this delta Tx is very large, what does it mean? It means that if at all I form a glass, this glass to crystallize, I need to heat it to very high temperatures. Unless I heat it to very high temperatures, it will not crystallize. That means the glass is a stable glass. When people are talking about bulk metallic glasses, what is important is how easily a glass can form, and at the same time how stable is that glass. Both are important. I make a glass, I have to keep that glass as a glass without it transforming into a crystal for a long period. So that is why stability of the glass is also very important, and this is a indicator, it is a parameter which indicates the stability of the glass, delta Tx, which is called supercooled liquid regime. That means that temperature regime or temperature range in which the liquid, supercooled liquid, can exist before it crystallizes. So glass transforms to a supercooled liquid, and this supercooled liquid will take some time for it to transform to a crystal. What is that period? What is that period in terms of the delta T is what is crucial here. So that is what we are talking about. So you can talk about glass going to a supercooled liquid. Now let us come to what are the criteria of glass formation. There are a number of criteria people have proposed, starting from criteria based on phase diagrams, and we will come to one by one. For example, the phase diagram criterion, let us look at it. This is what tells you deep eutectics. Whether a eutectic is deep or shallow is what is decided by this criterion, which is called the phase diagram criterion. What does it tell you? For example, you choose a eutectic phase diagram. It is important to know one thing, that you get glass only when you have eutectics in a system. If you have isomorphous, then it is very difficult to get a glass. Please listen carefully. I still say it is very difficult to get a glass. I have never said it is impossible to get a glass. So if you want to have a glass very easily, you have to have eutectics in the system. If you have peritectics, no, it is not easy. Peritectics usually are situations where the liquid stability range is very limited. If you have a look at a peritectic phase diagram and compare it with a eutectic phase diagram, you will see in a eutectic phase diagram the liquidus comes low. When you add B to A or A to B, the liquidus decreases. That is the meaning of eutectic. What is the meaning of eutectic? Eutectic means low melting. So that means the melting point decreases when you add A to B or B to A, and so that means the stability range of liquid is higher in a eutectic when compared to a peritectic. So that is why eutectic are the systems where the glass is easy. But among the eutectics, how do we say which eutectic can easily form a glass, which eutectic cannot form a glass, or which eutectic is more difficult to form a glass? Okay, is depends on this parameter. For example, if you take the two pure metal melting points TLA and TLB and use the rule of mixtures and calculate what is that called TL mixing. That means the melting point of a mechanical mixture of A and B of a certain composition, which is shown by this point there. The melting point of such a mixture is given by any point on this straight line, the dotted straight line. That will give you the mechanical mixture melting point, isn't it? So I am choosing the composition which is the eutectic composition. At the eutectic composition, if I want to know what is TL mix, I find out what is the eutectic composition in terms of XA and XB, put it there, I get the TL mix, and from that deduct the TE. Here instead of TL we should put TE actually. TL here is the eutectic temperature. But why we are putting TL means this is applicable not only for the eutectic composition but for any composition. If I choose some other composition, either hypoeutectic or hypereutectic, then for that composition I choose that particular TL mix minus the TL corresponding to that composition, and that difference is what is called delta TL mix. That divided by the TL mix for that composition will give you a parameter called TLR. And if this parameter is larger than a certain number, that number is here given 0.2, which is given by Donald and Davis long back, and if TLR can be higher than 0.2, then you will get a easy glass former. So easy glass formers are those where the TLR is greater than 0.2. And wherever the TLR is less than 0.2, we can say they are difficult glass formers. That means if you want to get a glass there, the critical cooling rate is higher for such a glasses. That means if you use higher cooling rate, you may get a glass in those systems, whereas in these compositions or in these systems where TLR is greater than 0.2, the critical cooling rate is low. Then let us go to the other criteria. What is it? One is the TRG criterion. What is TRG? TRG is nothing but TG by TL, the glass transition temperature divided by the liquidus. And if this value is greater than about 0.6, Turnbull in 1969, he was the first to postulate a glass forming criterion, and he said if the TRG is greater than 0.6, TRG is called reduced glass transition temperature. That is why the letter R comes there, reduced glass transition. That means we are normalizing the glass transition temperature with respect to the melting point. For example, come to this phase diagram. I choose any composition here and the glass transition temperature is somewhere here below the eutectic, and I take the glass transition temperature divided with the liquidus temperature, that fraction is what is the TRG. And if I compare for various compositions, I can easily see that TRG will be the highest for what composition? For the eutectic composition, because for the eutectic composition TL is lowest. So in a TRG the denominator is the lowest, TG is more or less constant, TG does not depend on the composition much, TG is more or less constant in a phase diagram, whereas TL can vary. TL is the lowest at the eutectic. So if because TL is the lowest, so if the denominator is the lowest, the fraction will be the highest. So at that eutectic temperature the TRG is the maximum. That is why eutectic compositions are the easy glass forming compositions. If you want to get a glass, you look for the eutectic in the phase diagram. So find out all the phase diagrams identify where is the eutectic composition, and among the two eutectic phase diagrams compare the TLR and choose that particular system which has a higher TLR, you have a greater chances of getting a glass in that system. That is the second criterion. The third criterion is delta Tx, as I told you. So, the larger the delta Tx, the easier the glass former, the higher the stability of the glass. And also you have the 4 Hume-Rothery rules which also form part of this glass forming criteria. One is the size factor. We know that if a solid solution has to form, the size factor has to be very small. If it is less than about 15%, we say glass can easily form, solid solution can easily form. But if it is higher than 15%, that is when you can form easily glass. In fact, here we have put down all these criteria in the form of a table, and you can see the atomic size difference is one of the first and foremost criterion, which shows that if the Ra by Rb, atomic radii of A and B, are greater than 12% or less than 0.88, that means if the ratio is greater than 1.2 or less than 0.88, that means if the difference is greater than 12%, then you can easily get a glass. And there are a number of examples where such a situation exists and you can get glasses very easily. Iron boron is one of the very crucial examples for that. Palladium silicon, gold silicon is another. And then the next thing is the structure. We know if the two elements have the same crystal structure, then you will never get a glass. It is almost very difficult to get a glass. It is very difficult to get a glass because it is an isomorphous system. If A and B have the same crystal structure, you end up in an isomorphous system. So, it is very difficult to get a glass if A and B have different crystal structure, if I have the same crystal structure. But if they have different crystal structures, then it is more easy for the formation of the glass, because for the crystal to form in a solid solution or in the form of an alloy, it is more difficult. And the more complicated the crystal structure is, the more easy the glass formation. That is why we have seen that in silicate glasses it is very easy for a glass to form, whereas in pure metals it is more difficult for a glass to form. Then the valence factor, and this is what you can see here. If the valence difference is greater than about 4, then you can easily get a glass. And the reverse is what we are talking of solid solution. When the valence of A and B are similar, very close to each other, then we can get easily solid solution. When the valency difference between the two is large, then you get you don't get a solid solution, and there is a chance for getting the amorphous phase or the glass. So, wherever the criteria are not favorable for a solid solution formation, then you have the criteria which are favorable for the glass formation, because if at all a solid solution can easily form, then glass would not form. Then the liquid would tend to become a solid solution rather than becoming a glass. So, wherever solid solution is more difficult to form, then the liquid would undergo a glass transition more easily. So, this is one, and the final thing is the confusion principle, we say, which is one of the very common phenomena or common feature nowadays in most of the new glasses that are formed, which are called the bulk metallic glasses. Bulk metallic glasses are those where the glass can be obtained in bulk form. We talked about it in the last two classes, and such glasses are possible only when you put a large number of elements into a system, into an alloy. For example, there are bulk metallic glasses which have 5, 6, 7 number of components in them. If you introduce so many elements into the alloy, then formation of a crystal structure becomes very difficult, because all these elements have to sit somewhere in the unit cell. So, that becomes very difficult. So, there is a kind of a confusion in the liquid of what kind of a crystal structure it should choose when you have so many elements in it. And in such a circumstances, under those circumstances, liquid would easily become a glass rather than becoming a crystal, and that is what is called a confusion principle. And so this is possible when you increase the number of components. That is why multi-component alloys are easy glass formers. We will come to it a little later when we talk about bulk metallic glasses. So this is one of the important criteria which people consider nowadays whenever they want to make a bulk metallic glass. It is almost next to impossible to make a bulk metallic glass in a two component system. In a binary system, nobody could so far achieve a bulk metallic glass. It is very difficult. Even if all the other criteria are satisfied, if you want to really make a glass in a thick form, then you need a large number of elements, so that you make the liquid very viscous. Once you make the liquid very viscous, diffusivity is very much restricted, and that is when the crystal cannot form. So liquid will become a glass. Why is that silicate liquid is becoming glass very easily? Because liquid is viscous and the crystal is more complicated. So both of them are making it easy glass former. That is what people are nowadays using it in the metallic systems also, making the liquid more viscous by introducing large number of elements, okay, which make the liquid very viscous. So, and the other criterion which Turnbull in 1976 postulated is what is called T0L minus TL criterion, where T0 is given by this expression, where delta HF is the what? Delta HF is enthalpy of fusion or latent heat of fusion. Okay. For the A is the solvent atom. Here we are talking with respect to a solvent atom A. If A is the solvent atom and B is the solute atom, we take the delta HF of A and the melting point of A, divide it with delta HF minus R, which is the gas constant, multiplied by ln 1 minus x, where x is the solute concentration, xB into Tf. So 1 minus x is nothing but xa. So this parameter minus the liquidus temperature divided by the parameter once again, if this fraction is greater than 0.09, these are all again mostly empirical rules. They have found that in a number of systems these things are valid. So they say that yes, if you find out that this is valid, then you can get a glass very easily. So this is another criterion which people use very regularly. Then valence electron concentration, we talked about valence difference. If the valence electron concentration is very large, you can get a easily glass formation. Complex equilibrium phases, if the structure is complicated, such as Frank-Caspar phases, you can get easy glass formation. The examples are given here. Deep eutectics, where the TRG is greater than about 0.4, then you can get a easily glass formation. Palladium silicon is an example there. Iron boron is also another example. Gold silicon is another example there. Confusion principle, when you have a large number of alloying elements, for example, you have a 5-component, 2 5-component examples are given here. All these are various glass forming criteria. Recently, there have been a lot of interest on bulk metallic glasses, and people started looking at these glass forming criteria very closely and looking at the correlation between the various criteria with the experimental parameters. RC is, what is it? It is a critical cooling rate for the glass to form, and this Tmax is the maximum thickness that you can achieve, which is a glass. This is similar to in a martensite formation, we talk of a critical diameter. Whenever we talk about hardenability, we give hardenability in terms of a critical diameter. That means that what is the minimum diameter where you can get a glass, you can get a martensite throughout the section. In fact, the best way to define is 50% martensite at the center. That is how people define it, because it is impossible to identify which is the region where 100% martensite is. So the critical diameter there is an indicator of the hardenability. If the critical diameter is larger for a particular composition, then we say it has a higher hardenability. If it is very small, then we say it is not really hardenable. Similarly, if the T max, which is the maximum thickness over which you can get a glass very easily. How people find out this? There is a very easy way to find out. Nowadays what people do is take a liquid and pour it into a tapered mold like this, tapered copper mold, and once you pour the liquid, once it is solidified, you take that casting which is of this shape and then section it vertically and then look at the structure from the tip upwards and see what is that distance up to which it is completely amorphous, what is the diameter up to which it is completely amorphous, beyond which some crystals start forming. This is similar to what is we use in hardenability testing method. What is that testing method? Jomini end quench test. Exactly. Similar to Jomini end quench test, this is a similar test. So when you pour this liquid and then section it and look at the structure, even in an optical microscope many times you can see crystals forming here. Otherwise you can go to TEM kind of situation or do an X-ray section, various sections, small thin slices, each slice subjected to an X-ray diffraction. That means vertically you keep on sectioning them, horizontally you keep on sectioning them, a number of sections, each section can be subject to an X-ray and find out, or vertically section it, look at it in a optical microscope or in a CM and identify if there are crystals. So wherever there are crystals, that particular diameter is the limit of the glass formation. So we can define what is called critical diameter, and that is nothing but the T max. So for each composition one can find out this, and this if you correlate with the TRG, you can see that there is an inverse correlation between RC and TRG. As TRG increases for any particular system, then the RC will decrease. That means that if the TRG for a alloy is very large, the critical cooling rate is very small. That means it can become a glass very easily. All those bulk metallic glasses are those which have the TRG greater than 0.6. That means this domain. If you put 0.6, go vertically up and find out, and this hatched region is the region which is the region for the bulk metallic glasses. And what is the cooling rate corresponding to that? It is less than about 10 to the power 3 Kelvin per second. In fact, all those bulk metallic glasses are those where the cooling rates are of the order of 100 Kelvin per second or lower than that. If the cooling rate is more than that, then we don't really call it as a bulk metallic glass. So bulk metallic glass, if you want to crudely define, is a glass which can be obtained at a cooling rate less than about 100 Kelvin per second. So if there is a composition where you can get a glass at that low cooling rate, then you can call it as a bulk metallic glass. And correspondingly the thickness would keep on increasing if you increase the TG by Tm. If the TRG increases, then you can see the T max increases. And there are a number of systems which have been shown here, which are examples here. The cobalt based, nickel based, iron based, palladium based. The best alloy is the palladium copper nickel phosphorus alloy, which has a value of T max of the order of around 100 now, 100 millimeters people have obtained very easily. And the other criterion is delta Tx. Again this also has an inverse relation between RC and delta Tx. If the delta Tx is very large, then RC is very small. So for a system where the delta Tx is very large, then you can say then the RC is very small. So one can have a glass formation very easily. And again all these glasses can be clubbed here and one can identify what kind of a plot it is. These are all bulk metallic glasses. And there are a number of such criteria, and these are some examples. One can find out the delta Tx for various compositions and plot what are called iso delta Tx plots. That means identify all those compositions where the delta Tx is the same and connect them with a line. And so each line here, each circle there you are seeing an elongated circles, they are all ellipses, and each of them corresponds to one particular delta Tx. And you can see as you keep on going to the interior circle, the delta Tx keeps on increasing, and one can identify a particular composition where the delta Tx is the maximum. So that is the particular composition in this phase diagram which has the highest glass forming ability. So one can do this kind of things either in terms of delta Tx or in terms of TRG. This is another such system where the delta Tx is plotted. This is for 40K, this is for 50K, this is for 80, 90, 100 and 120. This small domain is for 120K. That means that those are the compositions which are there within this small domain which have the highest glass forming ability. So one can identify the compositions. But the only restriction here is for identifying which is the best composition, what we have to do is first we have to make a glass. You have to make a alloy, make it into a glass, then heat this glass, get the Tg and the Tx, identify what is the delta Tx and then plot it. So that means this is what we are doing, a kind of a post-mortem. We have already made the glass and then finding out among all these compositions which has the highest glass forming ability. That means this is not a real predictive type of a way of finding out which is the best glass former. But the advantage with to some extent with this system is one can make a lot of compositions and rapidly solidify them by using melt spinning and get ribbons, and each of these ribbon they can do easily the DSC and find out this. In fact, there is a group in Japan, one Professor Inoue, his students, each one of the student takes, he has about 50 to 60 students, research scholars, okay. Each one of them looks at one ternary, they make hundreds of alloys, and within a few days it is very easy to make these alloys. If you have an arc melter, you can just make it very easily, and if you have a melt spinner, I have made 16 alloys in one day and did X-ray of all 16 of alloys, identified whether they are amorphous or not, and then did DSC of all of them and could find out what is the delta Tx. This is all just starting from weighing the sample, okay, to making an alloy and doing melt spinning and then finally finding out the delta Tx. All this I could do just within 24 hours, 16 alloys. This is possible. Okay, there are a number of people who do all this and then identify that. But then what is the advantage that you get? The advantage that you get is you can identify the composition which is the best composition and take that composition and make this kind of a bulk glass. Okay, you can pour it into a mold of a cylinder of a particular diameter and then get a easy glass formation. So before doing that you can do melt spinning. But nowadays we are talking of predictive type of models, how to predict which is the best glass without doing an experiment. So that is where lot of people, we ourselves are working on that, doing thermodynamic calculations, finding out where is the delta H mixing is the maximum, highly negative, because we know that if the heat of mixing or enthalpy of the liquid is highly negative, that means liquid is more stable. So if you can stabilize the liquid, you can make a glass. So identify that composition where the enthalpy is highly negative, which is one can easily calculate it using thermodynamics. Once you calculate that particular composition, one can take it and make a glass and show that yes, this is a easy glass former. We will stop here and continue in the next class.